Hi, everyone. So good morning, and thank you for tuning in. This is lecture 12, and we will learn a little bit about some workflows that we have developed to bridge between experiments with theory, particularly with some ensemble networks that could connect to performing atomistic simulations. So all the materials of the lecture is available to you from the GitHub page, and you could follow the slides from there, or just like see the screen that I'm sharing. So today's lecture or tutorial will be divided into two parts. The first part, we will learn about going from microscopic images to extract the information about atom types, coordinates from that. And then we will do some hands-on tutorials with like notebooks to see how we actually perform or implement those type of workflows. And then the next part will be thinking about, and we will come back to the slides to see if we are able to extract some of the features from the images directly. Is there a way to pipe that into a simulations environment to perform atomistic simulations? And that could be some first principles techniques like density functional theory, molecular dynamics, to look into materials properties, but not only predict them or estimate the properties, but how we could even utilize information that we get from there as a feedback to guide next set of experiments. But before I dive into the workflows, just a quick reminder on the things that you have already learned in the previous lectures. Working with image data, it's not always easy because a lot of the times we have access to a lot of data, but they are unlabeled. And in today's examples, we will see how we are still using this unlabeled data to get to the feature identification. So the idea is to go from experiments, the noisy images, and then get to the neural network outputs that would look something like this, where you have the information on each of the individual pixels representing some atoms or defects and so on. So, but while we are doing this, while we are extracting this type of information, we have to keep in mind that we are trying to study some materials under electron beam. So therefore, understanding the materials physics and what's really going on is very important. But the traditional way of doing that is to probably perform some experiments and then go back and perform some simulations and perhaps come back together after a few months to do some comparison between the experimental results and the results that we get from theoretical simulations. So is there a way to connect this in the loop on the fly, such that you could bring in the theoretical understanding and connect that with the experiments combined with the machine learning? So that's what we will be focusing on in today's lecture as we proceed. All right. So as I mentioned, the first part of the tutorial will be focused on one of the workflows on ensemble networks. And I think in the previous lectures, as I've seen the materials that we have gone through, you have already known that the deep learning strategies that can be applied to successfully categorize different natural images into different classes. Because each of these classes generally contains thousands of samples with large variability. Therefore, the typical networks to perform classification tasks perform really well. But in our case, when we are dealing with, let's say, images generated by scanning transmission electron microscopy, the idea is to find or identify atom particle defects. They essentially look the same. So we are trying to find nearly identical objects. But now more so, the difficult part is, let's say you perform an experiment on one day on a graphene sample or an MOS2. And then the next day, your imaging conditions might have slightly changed. So how do you, and you have trained the network on the previous day to extract some information. How do you adapt to that changes that have happened and that cause essentially the data set shifts and out of distribution drifts in the data? So how do you account for that? And this is also applicable to data coming from simulations, because you can tune in different parameters in your input files when you run the simulations. So, and that could give you changes that were not considered in the previous distribution. So in general, the feature finding here becomes much more challenging. That's where ELITE comes into play. So what we will see here is the first initial training data is being constructed by simulations. So why so? Because to remind you again, maybe we have access to experimental data, but it's probably unlabeled or weakly labeled. So we cannot directly use it to extract the information at the first place. So how about we try to scavenge some data from simulations, maybe from existing databases, or perform the simulations by ourselves to construct a broad distribution of data, and then train some ensemble of networks, and then utilize that to see if we can decode some of the information from the experimental data. But at this point, we should realize that the simulation data is essentially, we are assuming that it's a broad distribution of data. Therefore, we will only be able to reconstruct some of the images, some of the features. But at that point, we can refine the training set again, and then retrain the ensemble of networks, perform this in an iterative fashion to get to robust feature finding and quantify the uncertainties. In the ELITE framework that we will also take a look while we do the hands-on tutorials, we will be using the unit type of models. So the idea is to go from some noisy image, and this could be coming from the simulations, or if you have a previously labeled experimental data, that could also be utilized. And the output should be the semantically segmented map as shown in the right. So this is how the algorithms sort of look like. We train the ensemble of models, apply the ensemble of models to the experimental data. So you have multiple models that you apply. And then that's where the human in the loop can come into play to choose an artifact-free model, such that you're not essentially picking a model that have picked up some unphysical behavior or features, and then utilize that to refine the training set, train the new ensemble of models, and apply that back to the real experimental data. And we could also go from a single class to a multi-class training set and train the ensemble of models again to get to features, let's say, where you have multiple atoms present in your system. All right, so before we go to the hands-on tutorial, I just want to show some of the, like very briefly, some results. So these are snapshots of the simulations data. So what we did, we took 200 atoms graphene supercell, and then we perform an ab initio molecular dynamics calculation at 300 Kelvin. And in every iteration, we took out one atom and then perform the simulations again. Once we have the simulations, then we utilize that to build a training data set, and we augment the data such that it more or less sort of represent how the experimental images may look like. And then that's how we construct our initial training data. And we will see like a notebook where we could do that, and I'll show you how to do it. And then the next task is to utilize that to train ensemble of models and then apply that to the real data. For this case, the real data is a graphene image movie where we have 100 different image frames. And you can see more we progress, let's say from frame 1 to frame 90, you have more defect regions because electron beam has hit your sample. Now, once we apply the ensemble of models just trained on the simulated data, you can see some of the carbon atoms have already been detected, but there are regions that are not been reconstructed fully. But we can use these predictions and then go to the first iteration of training the ensemble of models again and utilize that to get to the mean deep learning prediction that would give us a better or better prediction or better accuracy in feature finding. Now, in this step, the idea is to bring in human in the loop to choose one of the ensemble of models that would have an artifact-free feature extraction available. In the next case, since we are essentially utilizing more or less the same distribution now, while we have already refined the training data, then taking the mean of the ensemble models prediction makes more sense. And then we can adapt to a multi-class segmentation model as well to train the ensemble of models again to get to the prediction of the atoms or the defect types, in this case, carbon and some silicon atoms, and then estimate the uncertainty in the ensemble predictions on the level of individual pixels. So the main takeaways from here is we go from the microscopic images, and then we go to the feature extraction. But here we could utilize the ensemble of networks to have these models as pre-trained models that we could keep. And then one of the recent papers have shown how we could even utilize the pre-trained elite models on the fly to detect features from graphene samples, and that was the imaging conditions were different. But now the experimentalists could detect the features on the fly because the network is able to adapt to the newer conditions and then find different defects, let's say the 7-member ring or the 5-member ring defects and so on. All right. So the next step is to go and get dirty and do some notebooks. So the first section will be the data preparation, and then the next will be training some elite models. I just want to, while you are maybe pulling your notebooks from the GitHub page, you're also welcome to see, to ask me questions or just feel free anytime. So the first notebook we are going to go through is the notebook _1. Is everybody with me, or is it too early in the morning? I want to hear something. Or maybe in the chat, I don't know. Is everybody still with me? Very quiet. Okay, cool. Excellent. Okay, so we will start doing the notebooks now. So this is one of my, so this is lecture 12. Somebody asked a question. This is lecture 12. We were just going through part of the slides, and then we will, then now we are gonna do the notebook 1. So the training data set that we, of course, generated had a lot of data, and our collab notebook memory will flood if we want to do that right now. So I will just show you still how we can repeat this process, but with like few files. So first we install some packages, and that should not get take much time. Okay. And then that's the importing libraries. This is an important thing. So all the files that we download is available to you through a Dropbox link. So this link is there in the notebooks. Just in case if you have any, you should not have any difficulty to download the files. But in case if you have, just let me know. We will work around. Okay, so the files that we are going to download is 4 files. So it's the, you call it the XDATCAR files. Okay, so where do we get it? So if you perform ab initio molecular dynamics simulations using VASP, so that's a very well-known package that we tend to use in the first principles community. You're going to get this type of files, which are called XDATCAR. So what does it contain? I just want to quickly show you. So this is almost like a text file you can think of. So you have the information about the lattice, so the lattice parameters, and then you have run the molecular dynamics, the ab initio MD with it. So for every time step, you have the coordinates, and these are the fractional coordinates. So you can just multiply this with your lattice parameters, so to get to the XYZ coordinates. So for every single, whichever many molecular dynamic steps you have performed the simulations for, your coordinates are available to you. And this is called, you can call it like a trajectory, right? If you, and this was done for 300 Kelvin, where you may not need like a rescaling of the velocity or anything like that to make sure your temperature is constant. But if you are running like, higher temperature simulations, then you may have to rescale the velocities, and there the file kind of writes in a different way, where the coordinates are kind of appended, I think, in every like 10 or blocks or so on, depending on what you have suggested or what you have given as the input parameters to scale your velocity to keep the temperature constant. All right, so these are the type of files we are going to use, such that we can extract all the information from each trajectory. You can also essentially utilize, the initial or the final coordinates file, but that kind of, makes your training data that is available to you much lesser. So that's why we want to utilize all the trajectories. Okay. This is a step sort of optional, but I like to do this because I like to keep my stuffs with my Google Drive a lot. So it's up to you. Okay, so then we define some functions that will read in all these position files with coordinates of atoms, just like I have shown it, and then generate an augmented data set. Okay, so what does that mean? So you have these coordinates file, and if you just open it, then you will see, if you go back to our slides, sort of this is sort of it would look like perhaps in the Vesta or other visualization where you have the positions. Then you utilize, so you extract this information for every trajectory, and then you append the coordinates information, and then you multiply that with the lattice parameters to get to the Cartesian coordinates. And then you essentially fit a 2D Gaussian mask around every atom, and then you can change the width of this and so on. And then essentially generate the mask. And even though I am showing you for like a pure carbon simulation, so this is only like pure graphene, we have recently done this for MOS2, so which has multiple atoms, and this still works. Okay. So that's what it's doing here. Because of the memory issue and all of that, I'm just utilizing like the 30 trajectories but in the main data set, we have utilized, we have taken the full trajectories, all of them. There is one parameter that is very important here, which is this angstrom to pixel conversion coefficient. You can try to play with it as well. Okay, so once you have that, I'm just a very careful, and also I like to check my steps everywhere, so that's why I print stuff more. Okay, so this is what your simulated image looks like with, after you have fitted Gaussian 2D Gaussian masks around that. And this is your mask where you have the carbon atoms, and then the label, you have the one for all the carbon atoms. Now you see that there is a question, or I am, which code, like, are you mentioning about? I mean, the tutorial itself, like the notebook, or can you explain that? Okay, while we are getting the answers. So once you simulate the image and the mask, you see that there is a lot of empty space, and that does not contain any information. So you could essentially go through some of your images picked randomly and see, where you could crop it, crop out the empty space, and then generate the so you just crop this out, and then you sort of have the region where you focused region where you have access to all the features, and then you can stack them. One thing we have noticed that if the image sizes are like multiples of 16, it's cool. So maybe keeping it to 256 to 256 or something of 16's multiple is a good choice. And then you can again visualize that. So we are not going to do the data augmentation here. We'll do it in the next notebook. But so far, essentially, we got from the simulations data. Oh yeah, sure. I'll explain the simulation part. No such file or directory. Did you run the? Did you get the the Dropbox file? Try to execute that cell. I think if you do, then it should be good.
Okay.
Okay. Yeah, make sure you execute this. Let me also make sure I copy paste this link to the Dropbox. Actually, should have done that before. So the simulation part, so as I mentioned before, the simulation was performed with VASP, with ab initio molecular dynamics. So we have run AIMD part with 200 atoms graphene supercell. And then at 300 Kelvin with the temperature constant. And then for every simulation, we also take out one atom each, up until there is like 10 or 20 atoms left in the cell. And then we gather that data. So all of the, let's say, XDA-TCAR files, so all the trajectory information, and then read that to generate our full training data set. You can also look into the simulation details more in the paper here. So this paper, where the K-point path and everything is also given, if you're more interested in that. But the idea is, like, what we are again going to proceed to is to what we are currently doing, this is a graphene sample, but what I have been working on is to generate pre-trained models for MOS2. And there we have actually performed simulations on different defects, and then also at different temperatures. So there it will be interesting to see if we bring in all the temperature dependent simulations data together versus having models that are only trained on a constant temperature. All right, so the next notebook that we want to go through is notebook number 2. So this is the elite notebook. So this is a little bit, this is going to take a little bit of time. And the full tutorial, I like the full elite models to get to like the multi-class segmentation, that is available to you through the elite tutorial itself in my GitHub page. But for today's course, I have just going to show you till the first iteration, which essentially gives you the main idea, because otherwise it will just going to take the entire time. Okay, so this is again, any more questions from the first notebook before I go to the second one? Any more questions? And this is not specific to like performing simulations with VASP. You could also have like simulations performed with some other packages, or not only AIMD, but just like performing DFT or so on, and just having access to the coordinate files, and then your game, basically you can use that to generate your training data utilizing this type of method. All right, so I'm just gonna quit this. If you have more questions, please feel free to use the chat box. And then, okay, so let's proceed to the notebook number 2 now. So I noticed one few things which I spent some time debugging the other day. The PyPy installation for Atom AI might not have like, probably, I don't know, there is like a difference. So there might be some errors that you will get from using some of the, or calling some of the functions. So just install it from the Git itself, and that just solves the problem. So I spent like 2 hours the other day fixing that. And then Maxime, who is the main developer of Atom AI, he's like, try installing this from Git, because this error has already been fixed. And I'm like, oh, okay. So okay, so our installation is done, and then you import some of the packages. Question. Invisible part. Oh, no. Okay. So then the next is to download the image data. So that's the image data that I've been referring to you, the 100 image frames of graphene movie. Yeah. Okay, so let's look at the image. One of the frames at least. So so there exist 100 image frames. So this is what it sort of looks like. It's like amorphous region, and then you have the carbon atoms. So we just to remind ourselves now, like, the simulations that the training data set that we just constructed, has no amorphous region. So, that's something what we are going to do and how the network is going to adapt. It's amazing. Okay, so this is something that you have access to, and this may take a little bit of time to download, where you have that full data set available to you, the cropped images with the masks for all the trajectories. So this step may take a little bit of time. So while that is downloading, I would like to just go back to the simulation part a little bit more, just to kind of give you an idea that you could also, and I think I have mentioned that before, that you could perform different type of simulations to get to generating your training data. But you could also do, so this is more like accurate. So this also takes time. Generating like a huge data set for, let's say, MS2 defect structures, going to take you like at least a couple of months, probably. What you can do also something like a more like a generalized simulation, like a multi-slice method and things like that. That you can also use. So it doesn't have to be very exact. The other thing I want to talk about while that is downloading. This important part, like as I mentioned, I think a little bit on the go, that going from when you're going from simulated data to the experimental data with this, then the human in the loop to pick and choose the model that has the artifact-free features extraction, that comes into play. That becomes very important. But if you already had some experimental data that you have trained your models on, and then you had the features extraction, then you can essentially try to see if taking the average of your predictions of all the ensemble of models will give you a good prediction. So that's something you can keep in mind. So here we essentially do not have any labeled data. It's all unlabeled. So that's why we are starting from the simulations itself and choosing some ensemble of models. Okay, almost there. Okay, so that's downloaded. So let's look at what we just downloaded. So this is just you have like 6,000 sort of simulated images and the masks from the data, from the AIMD data. Okay. All right, so now we are going to, so this looks very accurate, right? And this is not how the experimental images look like, correct? So if you go back to the slides, this one kind of gives you like what the image should look like. So if you're gonna train your models on this, you may not have any luck. So therefore we do some augmentation. So we put some noise, we blur, zoom in, all that. I wonder why I haven't plotted this. Maybe I thought it was done before. So the other day I tried the generate with AI, this option. This is pretty smart. Okay. Let's try to just look at the thing that we just generated. Is there a couple? No, so you could just use a single type of noise or different types. It doesn't matter, but adding noise definitely would help to generalize the data more. Okay, let's try to just copy and paste. Yeah, this is what it looks like now with all the noises that are being added. And then this is your mask. Okay. Okay. So now we are going to think about training the ensemble of models. That's what I wanted to talk to you about while we were waiting. It's fine. Okay, we are just going to take a little bit of a few minutes. So the ensemble of models that we train here, we keep in mind that we are shuffling the training data and then the random initialization of the initial weights. But then we keep a constant learning rate such that the model can converge faster. Okay, so that's something I wanted to just mention there. Okay, so if you want to train from using the Adam AI trainers, so there is an option for you to train the ensemble of models using UNet or some other networks as well. And then this is sort of the architecture. And then you utilize your training data and to train different number of models. So here it's 20 number of models. So I'm not going to train the models now because of course it's gonna take a long time. And then you also need to connect to the GPU. And I'm not sure if everybody has access to the Colab Plus and stuff. Instead, what we are going to do, we're going to do a little bit of cheating, but this cheating is allowed here because this kind of also shows you how we can utilize the pre-trained elite models. So we have had the pre-trained model on the graphene data. So we are just going to download that. And when I trained this model, that was done with a older version of Adam AI. So we are going to adapt to the new version by sort of training an empty set of models and then just uploading the weights to that. Okay. So that kind of essentially serves two purposes of showing you how you can train a model, but then also try to utilize a model from before. Yes, initial weights and then shuffling the training data. So random shuffling of the training data. So in every ensemble of models. So this is where it is downloading the data. Sorry, the model, the pre-trained model. So again, this model was trained on the simulated data itself, okay? So no experimental data till now, just using the simulated data and then training this model. Okay, so now we are gonna start, you're gonna see some like epochs and stuff like that. Okay, so there is there are strategies that you can utilize for training the ensemble model. So you could do it from scratch. So the first model should always be from scratch. And after that, you can, to use your previous weights and things like that, you could use a baseline. But make sure your architecture remains the same, of course. So right now you're just training like an empty model. And then we are gonna just upload the weights from the pre-trained model to it. And this is, by the way, I think the exact same model that Kevin used in this paper that I showed you the example of, where he has implemented this on the fly to look into single defects with STEM for graphene models. And he has also done this for MOS too. And then the imaging conditions, I think, were different, and also the purpose was different. Like it looks into like it goes on and to actually generate the defects. Okay. So if you go to the actual paper of the elite, in the supplementary material, I think I have shown. So this main paper here, I've shown how all of this ensemble of models kind of have more or less the same accuracy score, like the IOU score. But the interesting thing that you will see now, when we applied each of the model to the real experimental data, that some of them has like unphysical features. So that's where the human in the loop comes into play. So you cannot really judge just by the accuracy score. You have to actually look into seeing which model can be still used for the next iteration. And we are working on keep on watching this space from our group. We are working on having some pre-trained models on like MOS2 and those type of materials as well for everybody to use. So hopefully that will be coming to you, or we will make that available to you soon. Like the ones these are available as well. So you could try to see if you have some graphene type of data. Okay, almost there. Sorry, I had to train 20 models because the pre-trained model had 20 ensemble of models there. So, but it's a good practice to see how it works. Okay, perfect. So now let's use this. So we are gonna essentially use the every model. So you have 20 models, and then you're predicting on the experimental data. So you can see how each of the model actually has done. So look, we cannot definitely use this. And then it's very interesting to see how, you know, the random initialization of the weights and shuffling has, you know, has an effect on this ensemble model's performance. So we are gonna just use this model here because, you know, it kind of shows even if the feature identification, of course, is not accurate. We knew that, but there's like an amorphous region, like a different contrast that you can see. We definitely don't want to use something like that where, you know, it doesn't make it has some artifacts and does not represent the regions at all. Okay, so let's load that model, and then we will use that. So again, this is a single model. This is like a pick and choose thing, and then we and you can do that again for, you know, for all the models if you're interested, and then we utilize our predictor to get the predictions for all the image frames and the coordinates. So what we get out from here is essentially the coordinates of the features that are being identified. And that will essentially be utilized to refine the training set in the next iteration, which we will do in a bit. Okay, so I'm just showing like 2 frames here. You can plot. And so this is like frame number 1, frame number 90. You can see a lot of hole that has been created. Okay. Oh, I forgot to delete this. That's fine. So that's where the version problem was coming up. Okay, so now you see that there is like a lattice region and there is like an amorphous region. So we want to, of course, identify the features where there are atoms present, so in the lattice region. And we could do that by, you know, doing some thresholding method because the contrast is different. So we have utilized the Gaussian mixture model for this. So this is sort of an optional step. So you need to kind of check if you know, both of the phases were present in the prediction of your ensemble model or not. So this is kind of a choice that you make. So I say why, because I see that there's a lattice and a amorphous region, and I want to focus my feature extraction on the lattice side. So, okay, let's do that. So now if you execute this, then it is going to perform your Gaussian mixture model classification on the coordinates such that you separate out and then we will see the lattice and the amorphous phases. And this may also take time, a little bit more time. But there are options for you in this one, AOI stat, to choose different methods. So there's like k-means clustering, mean shift, or thresholding to perform this optional step. or not you're not going to get this one for all the, perhaps all the materials that you work with. But for this one, since we have created, or there is amorphous regions, we have to be careful. Okay, so there were two components that we separate out. And then, so let's look at what it does. This is your lattice region, this is your amorphous, so we don't necessarily care about this. So we are gonna separate this out to filter out the coordinates corresponding to the amorphous space, and we're just gonna keep them here. So you can update the class, which we have done already. And then let's plot one of the frames to see. Okay. So this now becomes now we have gotten from simulated data. We trained ensemble of models. We chose one. We looked into the prediction. We performed some intermediate classification step to separate out the lattice and the amorphous phase. And now we are going to use this to refine our training set, okay? So that's adapting to the experimental data. So the first set of iteration. So we are going to generate the ground truth for iterative training. And we only actually we do not do this for the entire image frame. We actually just use like 20 of the image frames to generate our data. Okay, our training. And then, okay, so this is one particular point everybody asks, right? How big of a data you need, data set, and then, how much of the, let's say, image movies you would need. We are using only 20 image frames, but you could also extract patches. So you can essentially create sub images of different window sizes, and then you can merge them to create a bigger training set like we have done here. So even if you have access to only a few images, you can still be able to train and get some good predictions. Okay, so I like to just show the model architecture once, because I've mentioned this, that you need to make sure the model architecture remains the same, compared to what you have initially trained your ensemble of models with, such that you could ensure the use of the baseline approach, okay? So this is the UNet model. You have the convolution layers and the ReLU activation functions, the normalization, upsample block looks basically the same upside down. Okay, so now we are going to use this training data, okay, that we just generated. And again, this is utilizing the prediction on the experimental data itself from the ensemble models that were trained on the simulated data. And then we are going to do the same thing here. We're going to download a model that was previously trained, but you could again do this here. So you should have to change this to from baseline if you're doing it in the normal conditions. So we're just going to execute this cell where we're going to again train we're going to download that model that was trained with the older version, and then we're going to update the weights to that. So again, since we are just uploading the weights. We're not really training anything. That's why it's a scratch. But when you do this for the real time, then you should do it from the baseline approach. I have spent hours understanding and doing the both, playing with, so. And once this is done, then now you are not operating on a broad distribution of data anymore, sort of, right? Because your training data is not the simulated data. Now your training data is sort of like the prediction data that you had in the intermediate iteration. So that's why you can just utilize or take the average of the ensemble of models prediction. Sometimes there is, if you have big enough data, there might be, like, if you're still running it in Colab and stuff like that, or even in general, if there is like a memory issue and stuff like that, you have the batch option available, so the prediction can be done. And then that will solve that issue as well. So I think there was a line somewhere. Or is it still doing it? So here we have trained 6 models. So that was quick. And then you can also, so since you have the mean prediction now, you could also do the, plot the variance so the standard deviation for the individual pixel to point out the uncertainties. So see, now you have all the, carbon atoms available to you, the feature information. And then also the associated uncertainties. So from there, you could also, okay, so I'll just do this. So this is for the entire data set. So here you could also choose the threshold of, like, your intensities, like the coordinates that you plot. Generally, it's constant for, or it should be actually, for all the image frames. This is since it's doing it on the on the full set, it's taking a little bit of time, but that's fine. While we're doing this, actually, I want to go back to that little comment on the adding noise that was in the chat box. Actually, we have done, not for this data set, but for some other oxides, it's the BFO, where we have actually looked into the feature extraction, but that was only with the convolution neural net, and like did some like opening up the neural net and then looking into what type of feature is being extracted and how for like from every layer. We have done that, and then with respect to variation of different noises. So you can also check out that work if you're more interested in that. Okay, so now we have access to the predictions for the carbon atoms, so this is what the original frame looks like, and this is what we have now. Accurately, we can get the features for the lattice phase. Now, for this data set, we also had defects. So this is just me plotting different frames, image frames, because why not, right? So for this data, we also had defects. So the, like the silicon atoms were there. And that's the next part of the tutorial, which I'm not going to go through because it's essentially doing the similar thing. It's just a multi-class segmentation mask that we're gonna make, but that is available to you through the tutorial from my page. But essentially, you will see by the end of it, and that's essentially the elite, the original paper, that we start from a simulated data that was only trained on carbon atoms and not necessarily any defects were there. We were just pulling out different atoms initially. And then we went from that to predicting predicting the features that are associated with the carbon atoms and as well as the impurities. So that's something you could also do. Okay, so I think this is kind of end of the first part of the tutorial, and I hope we are kind of on time. I would like to see if there are more questions, and if not, then I will go back to the slides now, and then come back to doing some more of hands-on stuff. So let me know if you have more questions. Oh, maybe it's a good idea to give you the, oh, well, it's in the slides as well. So if you want the full, like, the multi-class segmentation part as well, you could look at the initial elite notebook, and then also the elite tutorial there. Okay. So let's go to, so this is where we were. Okay, so now we are going to go to the next part. So the next part of this tutorial is focused on the workflows, where and how we will learn how to transform these features like the atomic positions and types that we can get from the neural networks, and then pipe that into atomistic simulations to perform different simulations and estimate the material properties, and how we can think about using some of that to essentially provide good feedback to perform the next set of experiments. So this is where definitely the human in the loop again comes into play, while we are trying to learn the materials physics that are associated. But there are certain roadblocks in direct piping of this microscopic data into the simulation environment. There is a strong disparity in the time and length scales. And even though I will show you an example of the workflow today, which kind of tries to address that, and we have shown example how to do it. There are still a lot of things that need to be addressed, and we are working on that, and I will kind of give you a sneak peek into the future of what we are working on now. Okay, so thinking about disparity in the time and length scale. So how long it takes you to, let's say, take an image of graphene, just one image frame, versus how long it would take me to perform a geometry optimization on 2000 atoms unit cell or supercell. Probably the differences. It's like a few seconds versus several computational CPU or GPU hours. We can utilize some methods like DFTB and so on, but getting access to the potentials for other elements which are not necessarily always available. So that also kind of gives sets a lot of the limitations. So the idea is to be able to address this by identifying the regions of interest to perform simulations on in a timely manner, such that we can be able to perform this on the fly, going directly from the microscopic image to so the feature identification part, which we have shown recently. Like you have, like we did in the last notebooks, and then go extract the coordinates, build a simulation object that can be utilized for performing different simulations, and then understanding that performing those simulations in a timely fashion may not always be possible while we are working on doing this on the fly. So how do we, bring in human in the loop again to define some regions of interest to perform the simulations on, which would well represent the perspective that we are seeing under the electron beam of a single material. So that's what we're gonna be learning. So again, we are focusing on these data sets that we have performed our feature extraction on, and then using the Atom AI utils functions, we can now make the simulation objects and then perform simulation. So I have defined the regions of interest, and we will see how we can do that in the notebooks. But for now, I'm just showing you some of the results where we have done, once we have extracted that information and built the simulation object, we can perform temperature dependent AIMD simulations at 300 Kelvin, where you basically see not much reconstruction going on. But then if you heat up the sample, then you will see that there will be a formation of the Stonewall's defect. And then not only we could do perform simulations like this after we have performed the geometry optimization at 0 Kelvin. The idea is to also be able to track the uncertainties, in the physical space, sort of. So, tracking the displacement of atoms, the bond lengths and the angles, and then such that we can compare the uncertainties associated from, going directly from the microscopic image to the simulation object, and then what the simulation would give us. And then we could also perform additional simulations to, let's say, think about or look into the dopant effect. So if you have had like some chromium atom and then placed in like the top hollow sites, how would your absorption energies change? Same with the graphene healing effects, because these are some of the phenomena that we can observe under the electron beam. So essentially what you see once you keep on heating the sample, some of the graphene after some time will start to heal by itself. So essentially the hydrocarbon molecules that are present in your environment, that is getting absorbed into your system. So how do we replicate that? using part of this, simulation object that or regions of interest, let's say, that we have identified from the image itself, decoded by the neural network. So that's what we have done in this, where we had different initial configurations where we have broken the bonds and then had the CH, CH2, CH3 molecules, and then perform AIMG simulations to see how how it gets reconstructed, and then how the defects begin to propagate to form, let's say, the Stonewall's defect, and then tracking the bond lengths at different temperatures, and then also quantifying the average errors in the coordinates along in the XY plane. That is what we see under the electron beam and also in the simulations, right? And then we will see that from the simulations that the graphene holes may have healed completely or partially. In all cases, also depends on the energy landscapes. And then interactions of the molecules with the edge atoms can still be observed. So we do terminate the, because we took the region of interest like a part of that perspective that we were seeing, we do have the hydrogen terminations. But altogether, there is a strong dependence of choosing an initial configuration of the atoms, right? Like where we have broken the bond and so on. And then, of course, the distances between the molecule and the surface, along with temperature. And while we were thinking about how you make that, utilizing the utilities that are available through the package, you could also, make your surfaces and then like put some vacuum and then put your molecules and so on. So there's lots of options available to perform the simulations that would give you estimate of the properties that you're interested in. So that's sort of the workflow that we're gonna see how we do that, from going from the image to the to performing simulations essentially. But using the pick and choose of regions of interest, because we cannot really perform the simulations on the fly at the same timely manner to give them a feedback signal. Oh yeah, place your dopant there, or do your defect construction, or hit your electron beam in this region to create this defect. But that's what we are working on now, while into the future, or more hopefully soon, where we are designing some theoretical proxies that would well represent the entire space that we see under the electron beam, and then that can connect to the target property as well as, of course, this experimental observables, so your microscopic image. And then also looking into the underlying physical mechanisms. And that's where, we are also going beyond the traditional way of performing machine learning, and just by looking into the correlative nature and identifying the different data-driven patterns. Instead, we also are interested in identifying the causal relations, which are more fundamental in terms of understanding what is really going on in the system. But here on, we have to be careful about, let's say the theoretical model that you have, let's say the phonon modes that essentially drive your phase transition are lead to different different properties that the material exhibit. You cannot always very easily quantify that with the experiments. So how can you represent those type of key elements from the theory, and that's where the idea of theoretical proxies come into play to relate to your experimental observables. So that's sort of a sneak peek into the future, and I think there is probably like a special lecture on causal ML from Sergey, and maybe I'll pitch in as well. I don't know, we'll see. So so that's what I wanted to speak to you about, like the slides, and here are the papers you could take a look if this is something interesting to you. And then so the next set of notebooks that we are going to go through is to actually perform this. So now the results that you have seen in these slides, of course, it's in this paper, but they were all done in the HPC environment. So I, of course, am not going to do this today, or I don't have the capability to do it. What I'm going to still show you is how you could still perform something similar using like an atomic simulation environment like AAC, which has a Python environment. So you could all do it in the notebook. So it's like running some cheaper simulations, but still getting the idea how you could go from image to feature your semantically segmented maps, which you have coordinates, and then how you pipe that to the atomistic simulations environment. Okay, so we will go to notebook 3, and then I put this as optional depending on how much time we have left. I'm guessing we will surely have time for 3 and 4. We shall see for 5. So if you have more questions, I had actually, so that's exactly what we are gonna essentially do. You will see that we have identified, pick and chose a set of region, and then we have made a, like a cubic cell, and you could do, there are options to make it more generalized. So you could choose your lattice type, and then you could also put in your lattice parameters, whatever you want. And make your simulation object. And this is sort of the example simulation. So it's like a toy simulation, you can think. You could use the Tursoff potential as well. I think that's the notebook 5, but the notebook 4 is just the Lennard-Jones. It's not gonna be giving us very good results, but it's just something that we will still do to show that it works. And then we will see that, how the atoms have moved themselves and reconstructed. So you can, before I go into this, you can see that, there were the defects, the blue atoms were the defects, so that were identified. So those are the information that we are using. Okay. So with that, let's go. Oh, why is it? Okay. And before I was thinking to come back to it, but depending on how much time, of course, the acknowledgements to the colleagues and mentors that I've worked with so far, Sergey and Maxime, and then Bobby, Stefan, and Rama. So I'd like to, of course, thank them for contributing. Okay. Let's do the tutorials if there are no questions. Or yes. Okay. So let's go to notebook 3. So again, the idea is you use the coordinates of the atoms that were predicted by your neural network, and then create a corresponding simulation object. And we utilize AAC because it is easy to use, and you also have an access to do it all in the Python environment, which is very convenient. Okay, so we are going to go through the notebook 3 now. So just installations. So some of the interactive things that come standard with AC is not available in the Colab environment, but if you have that locally installed, you could also see like the structures and all of that. So just to just a reminder there. So you may see like some structures are not moving. That is just because of the collab environment. And of course, there is a way to, if you have that AC installed in your HPC environment, you could connect that to your, VASP or some other LAMS packages as well to perform your simulations. This step is always nervous. It makes me nervous because a lot of the times there's like version problems, and then like one will install and one won't. Okay, so importing the libraries, and again, this is an optional step. Okay, so now we are gonna download the data. Essentially, we have the coordinates that were predicted by the ensemble networks, and then on the stem images of the graphene. So we are gonna download that entire data. Okay. So as I mentioned, you have access to the image data, you have access to the network outputs, and then the associated coordinates. So let's just for sanity check. That's exactly what we have been seeing, that data, and then the coordinates. Let's plot that. Okay. So you can see that, there are a little bit of defects there. So those are the, which were identified in the next set of that elite with the multi-class segmented model. All right, so this part is easy, or we have made it easy. So you have the carbon and the silicon. So you essentially just define a dictionary. So you can have multiple atoms, so you define the dictionary. Now there is the utils, in the utils function, you have, the class, you have access to the AAC utils. In there, you can utilize the basic option, or there is an advanced option. For the basic option, it essentially, all you would do is you take the coordinates, so the Adam AI or, the neural network predicted coordinates in the dictionary format, right? So let me just, so that's how it kind of looks like, your coordinates, okay? And then you choose your image frame, you call it whatever you want to call it, so it's graphene, and then you say, you have two types of atoms, so the carbon and the silicon, and then you provide your path where you want to save your POSCAR file, and then you also, and this is important, this is the angstrom to pixel ratio, and then that's it. you create a cubic cell of graphene. Now this is like again the basic version where you just put your coordinates in a cubic cell. What does it look like? Well, let's see. So if so that's sort of, and this is in the Cartesian coordinates. So you see you have 20, 21 plus 22 atoms, and then you have all of this atom position in the Cartesian coordinates. Okay, so that's basically what you were seeing right here, right? Like this. It's the upside down, but so that's what it would look like if you open that in your Vesta or other visualization. For the you also have the advanced option, as I mentioned, where you can actually maybe I can just show you that. Don't tell this to Maxime. In the middle of a tutorial going through Atom AI and to show you stuffs, but that's fine, I think. So you go to the utils, and then you go to the AC utils, and then you will have this basic option, and then you have the advanced. So in the advanced option, you actually can give your basically the Bravais lattice type by putting like the lattice vector in different three crystallographic axis direction, and then create your own simulation object. And here, actually, once you do that, you know, since this is an AC, it is an AC object. Now you have access to utilize all the other AC functionalities, like putting a vacuum or putting a different molecule on that, and it's very easy. So that's just what it is. Okay, so now, okay, any question up until this? I think not. So okay, so let's go. So once now we have created this object, now we are gonna use part of it, and that's where the human in the loop comes in, where we identify the region of interest and then perform some simulations. In the actual paper, we have utilized VASP for first performing the geometry optimization on that region of interest, and then performing the AIMD simulations. But here we are just gonna use some AAC inbuilt options to perform the simulations, just to show that it works. Optional again. Okay, so we are gonna download this position file, that, or the simulation object that we created using our utils function. And now we're just gonna perform like a very not good simulation, okay? But that's okay. Just to show that you can use this to perform simulations is good enough for now. So this is an example where we don't do the geometry optimization. So that option is also available to you. You know, you can use some quasi-Newton method and or some others. And for the using the AAC thing. And then this one, you just use the LJ potential. Of course, it does not work very well for the for the graphene, but it's just for an example, and we're just going to run this for like 5 steps, 25. Yeah. And then we can essentially save this trajectory and then make a movie out of that. And you can see, you know, things have broken apart because, of course, the potential was not very well defined. So obviously now the question is, how do we, if you are going to do this in the Python environment, how are you going to perform a more accurate, let's say, simulation? Oh yeah. So the prediction of the atomic coordinates. So there is 2 steps. One, the prediction of the atomic coordinates, utilizing Atom AI. When you're doing that, we had the simulation data as an initial training data. Okay. If you had access to some labeled data before, you could just use that to create the training data itself. So that's one part of the simulation, like related to the simulation. And the next part of this workflow, this is the separate workflow where you're like learning how to essentially use the network output to perform simulations. This is something, you know, if your task is to just identify features, you know, notebook 1 and 2 is good. That's where you end it. But we are material scientists, so we want to learn how, you know, how things are or why things are happening, and that only would come from the theoretical understanding, and that's where we go to the simulations and try to perform this or implement this end-to-end workflow on the fly. Does that answer that question? Hopefully. Okay, sweet. Okay, so now let's go to since we have a little bit of time. One more thing. So recently, as I've mentioned, I was working with MOS2 data. Okay. So the way the detection, so you're looking at a plane, so the sulfur atoms might be in the other plane, like the other sulfur atoms. So you're not probably detecting that. So when you're using that MOS2, you know, perspective or the image to create your simulation object, then it's not like the right representation of the material itself. So you have to make sure that you're identifying all the atoms correctly, even in the different plane. If not, then you have to kind of add in, you know, add in the atoms to make sure your coordination and everything is satisfied. Because otherwise you'll just have like something like a hexagon with MO and S2 in like sulfur in the same plane, which is not the right representation of your atomic structure. So this is not a very trivial way or trivial thing to do. So make sure you're seeing or you're identifying the atoms correctly and looking at the perspective to see what really is getting recognized. And if you're going to use this utility to create something, to create a simulation object, you have to make sure your coordinations and you know, the boundary conditions, everything is satisfied. Well, when you're doing this, then the periodic boundary condition is given automatically to you, you know, in every direction. So that may not be always true. So you have to keep that in mind. Okay, enough of my blabbering. Let's go to the optional notebook 5. So this is basically the same thing, but here we are gonna run the molecular dynamics with LAMMPS, okay, the Python environment. And this might have been a much more easier task to do it, probably if you have it installed somewhere within the HPC environment, which is probably will be the case if you're doing this in the real time, that you will have access to computers that can connect to your HPC. But since we don't have that, this is like an alternate way. So we are going to use a torus of potential, so it's a little bit better than previous. But this installation of the LAMS environment in the Google Colab, it's a little bit of a trick. So this trick is given to you, and hopefully today it will work and show its magic. It's going to take a little bit of time. So just please be patient with me, but I hope it will work. So in the while that is doing, I just want to quickly just refer to this paper here, where we have the focus was to identify the region of interest. So that's the part of essentially one part of that image and extracted features, and then performing the simulations and trying to learn about it, the material properties. We have also, and the idea was, since we cannot it is kind of, it's gonna take a long time to perform the simulation on like the almost 2,500 atoms, using the VAS for at that time the CPU. The GPU version is now available, and I think I'm hearing very good things about it. So hopefully that will solve our problem. But at that time, which was a year before, the GPU version was not fully stable and wasn't sure. So we were limited. So then we performed some DFTB simulations on the full graphene atoms for the full supercell. So that was like 2,500 atoms, and that really converged within few hours. So that is still a doable thing. Again, for performing DFTB, you probably are like the most of the parameters that are available is for like carbon or the hydrogen. So if you have like those type of systems, then you're really good performing the DFTB and using this workflow. If not, then that's where this a little bit of difficulty comes into play. And we are trying to also, of course, design this proxies, which hopefully will try to solve more problems associated with this disparity in the time and the length scale. Okay, I didn't want to show you this, but it's fine. Also, it's not while you're coding. It's probably better to see the errors or whatever is giving you than like, putting a capture which will just not show you anything. So that's something. You could also do this from like here, like the terminal, but any question or anything that anybody wants to mention? There's for the 3D systems, I think it's a little bit more it's a little bit more challenging because you're kind of looking at the 2D perspective of a 3D materials. That's where we are working on as well. Oh, yeah, that's an interesting question. Says, can I use these skills in quantum computing? All right, so my skill or my knowledge in quantum computing is a little bit limited, way limited. What I have tried is something like Q-skit-learn, where I have utilized different molecules to compare some energies. Doing that for solid state, putting the boundary conditions, I don't know yet. Maybe it has so the last time I did that was like few months before, so maybe there is already a way to that has been implemented to put in, like last time I wasn't sure how you put in the boundary conditions and so on to actually do the solid state physics. For isolated molecule, let's say you have like 10 or maybe 14 atoms, isolated molecule, you could do that. So I have some notebooks that would do it, but so that's my answer. I do not know, but yeah, maybe for molecules. Well, okay, so the elite, that is something, another thing. This elite framework has been implemented for also some soft systems like identifying protein nanorods as well. So doing this for soft systems has also been applied, and it has given us successful results. Perhaps. Anybody else wants to comment on that? This is a very interesting question. Collab makes your life easy a lot of the times, but then sometimes it's a little bit hard. So that's why I kind of kept it optional. So essentially what you will see is we will just run like the simulation, and some of the atoms would fly off. It's not still the the best representation. But for some systems, let's say, for which the potential is good, and it is just for like available to you, you could just use this for your for running the simulations instead of having to go to ask for CPU or GPU resources if it's not readily available to you. Trying to think if what else we can talk about a little bit more. You can talk about the causal stuff, but I I don't want to do that because there is there will be lectures for that later on. What we could We can kind of talk about a little bit on this, like tracking the errors. How is it important? So you could like kind of track, you could identify the atoms that you have created from your simulation object, and then compare that to the full image and the semantically segmented map out those atoms, make sure those are the same atoms, and then you can look into the bond lengths and which atoms have moved where and stuff like that, so such that you can actually identify which atoms have participated in the reconstruction of a geometry. For the simulations in this work, we have actually, while we were doing the structural optimization, we did, yes, I think so. I mean, as long as you can install the packages, and that should be easy to do, like a git clone. And yeah, you can run them for sure. So yeah, that way you can track which atoms have really participated in the reconstructions. For the geometry optimization, we had performed multiple optimization where we had, like, because we have terminated the atoms with the hydrogen, we had the hydrogen atoms fixed, and then doing the optimization on the carbon atoms only in the XY plane differently, like running selected dynamics and things like that. So that information is also available. Come on, 83%. Okay. Sorry, I could not find a better way. Like I worked on this multiple times to figure out easier way to do this in the Colab, but I haven't been able to. Oh, there used to be a package, or there is, I do not know, because I could not, there was like some version thing or whatever. It's called a Rebo. So those are the potentials that are also good. And there was a package that would just give you access to those potentials. But last time I checked, it wasn't really working. Again, that package had some issues. So maybe that has been fixed now, and you could use that and cross out this step. So to get access to the Rebo and Aribo potentials, which are better for this type of systems. Okay, so we are getting close to also the end of the 2 hours. So while we are waiting, again, the floor is open for questions and comments. Hopefully I didn't put you all to sleep. I do not know if we have shown this in previous tutorials, like the lectures, but so there is also a paper that we worked on, like, and that paper is available, where we have actually utilized this, Python dependent molecular dynamics environment to do some reinforcement learning, where we wanted to do like the targeted defects. So let's say having a silicon atom placed at somewhere in a carbon, in a graphene cell, and then how we could how that propagate, or the selective positions, how would that reconstruct the entire lattice, things like that. So that is something very interesting, where we paired the information that comes out from the molecular dynamics with the reinforcement learning strategy. There, of course, in the Python environment, we were using the Leonard-Jones potential, so we were criticized, and I agree to that. But that was the easy way to show that the framework works, which was our goal. It finally, it's done, complete. Okay. So that's just installation of AC. Hopefully it won't give us any trouble. Okay, good. This is the okay, so what we are gonna download is like a torus of potential for silicon carbon system that's available to you from the NIST website. So in the NIST website, there are multiple potentials. So you could just now pick and choose and have that inside your Python environment. Okay. Same downloading the simulation object. Again, this was a cubic cell that we assumed because it's just a basic one that we make for our example today. And then we will run the simulation. We will define our parameters with the potential, and then at 300 Kelvin, and we're just going to do some like very few steps. And the time step is like 1 femtosecond. It's like very minimum. Oh, see. Okay. Bye. Okay, so that didn't okay, so something went wrong for this one. I think it has to do, but I think this is a quick fix. Okay. It's probably here somewhere. I'm not gonna debug right now, but so once that runs, you can get to generating your movie, where you see like different molecular dynamic steps, and then your atoms are being reconstructed. Not sort of the most accurate representation, but definitely a good enough where you can think about how you can implement this type of workflow. All right, so with that, I'm kind of at the end of this tutorial or lecture. So I hope, while we were going through the acknowledgements, I just want to make sure that I hope that from lecture 12, we were able to kind of see how we can train ensemble networks to go from microscopic images to feature extraction, and that can adapt to different imaging conditions later on, and then use that type of information to pipe that data into the simulations environment. And this is sort of our way to connect theory and bring that in the loop of having this end-to-end workflow, connecting both experiments and theoretical domain to define or develop a comprehensive understanding of the material systems that we want to learn. Again, we are working on developing some of these theoretical proxies that would very well more rightfully address the disparities in the time and length scales. For now, the way we do it is to, bring in more the human in the loop to identify regions of interest that would well represent the system that we are looking at during our experimental characterization. With that, again, thank you so much for tuning in. Please feel free to send an email or, ping in the GitHub if you have more questions, if you come up with more questions, or I'm also there in LinkedIn. So, and I hope you're having a good time at the summer school. Bye. Okay, I'll just still stay till the end of the hour. Okay. All right. Bye, everybody. Thank you again for joining.